Okay, so welcome to today's lecture on operations research. Today we'll look at the linear programming. We'll continue with the previous lecture where we look at a single subscripted problem or model formulation. So in this lecture, we'll look at double subscripted linear programming problems. And so we'll go straight to the problem, some of the examples that we have here, then we'll look at some of the characteristics of a linear programming models. So let's go to, so this example that we are on for this week or this lecture. All right. So in this case, it says that a refinery blends 4 petroleum components into 3 grades. So 4 petroleum components into 3 grades. And let me see if I can get a pen here to do some to note some important keys here. So there's 4 petroleum components into 3 grades of gasoline, which are regular, premium, and low lead. Now, management wishes to determine the optimal mix of the 4 components that will maximize profit. So the maximum quantities available of each component and the cost per barrel are as follows. So we have the components 1, 2, 3, 4, and we have the maximum barrels that are available per day, and also the cost per barrel for each component. However, in order to ensure the proper blending for each gasoline grade, maximum or minimum percentages of the components in each blend have been determined. So the blends as well as the selling price of each are given in this table. So we have the grade, that's regular, premium, low lead, and we also have the component specifications. So for regular, there should not be less than 40% of component 1, not more than 20% of component 2, not less than 30% of component 3 in that order, and similar for premium, not less than 40%, and low lead, not more than 50% of 2 and not less than 10% of component 1. Then we have the selling prices, 12, 18, and 10. So how do we formulate this problem? All right, so we shall look at this model formulation in our whiteboard. So let me bring the whiteboard here. Okay, so for the first thing to do is always, so we talk about 3 things or 3 steps involved in the model formulation. That is decision variable, identification of decision variables. Then 2, objective function, that's the relationship between the decision variables. Then 3, the system constraint. So the first one is the decision variables. All right, so what are the decision variables for this kind of problem? Now, the company wants to know 2 main things. The first thing is what number of barrels of each grade that should be produced, and also how many barrels of each component should be blended to produce each grade. So it's a component that must be mixed together to produce a particular grade, and the number of grade or the number of the quantity of grade that must be produced. All right, so as such, the decision variable should reflect the quantity of each component that should be used in each grade, right? And there are 4 components and there are 3 grades. Okay, so what we'll do is that I will note here my components, which are 1, 2, 3, 4, and my grades, which are I'll use R for regular, P for premium, and L for the low lead. All right, so you can see there are 4 and 3. So what we'll do is that the decision variable will be, let's Xij, where I is the number of components. So the number of components. So components 1, 2, 3, 4, right? And J, let's say equivalent, right? So J is equivalent to the grade, where the grades are the regular. I can say R for regular, premium, P for that, and low lead. L. So let that, right, be the barrels of component I used in gasoline grade G per day, right? So you see that we're going to have, if we are to get the combination of decision variables, we are going to have 12 decision variables. What are they? So for regular grade, right, we are going to have Xij, which is X1R, right? Let me use semicolon here. X2 in R, X3 component in R, then X component 4 in R, right? Then when we take premium, the decision variable still Xij or X1 in R, right? Sorry, it's P. It's P, yeah. In P, X 2 in P, X3 in P, then X4 in P, right? Then the low lead is also Xij, right? Which is X1, component 1 in L, X component 2 in L, X component 3 in L, and then X component 4 in L. So you can see we have 4 decision variables for each grade, and therefore 12 total decision variables. 12 total decision variables. Now we look at the second one, which is the objective function. The objective function. So what is the objective function? Now, the objective function is to maximize the profit. Now we're given selling price, and we are also given the cost. Therefore, profit, as we know, right, So let me maximize the space here. So profit is the selling price minus the cost, right? Selling price minus the cost. So let's say cost price here. Let me add it. So selling price minus the cost price. So the selling price of regular is known to be $12 per barrel, right? The selling price for premium grade is $18, and that for low is 10. And the cost for component 1 is 9. The cost for component 2 is 7. 12 is the cost for component 3, and the cost for component 4 is $6 per barrel. So to maximize the profits, right, which is the objective function, right? So we can say maximize Z, right, which is actually the profit. So we should get the selling price. So let me take it from first principle, selling price minus the cost price, right? So in terms of the selling price, we are selling the 3 grade, right? So $12 is for regular, plus, let me say dot here, times regular, then 18 times premium, plus 10 times low lead, right? Then minus the costs. So we have 4 costs here. So 9 times component 1, let's say component 1, plus 7 times component 2, plus 12. So this is for us to appreciate how we can derive this, right? Yeah, we could have done this straightforward, but just for us to understand what we are doing for component 4, right? So what the decision variables for the regular? So we have these are decision variables: x1r, x2r, x2, 3r, x4r, right? Remember that at this stage, right, we could have also said that if we are using, instead of using R for the regular, if we are using 1, 2, 3 to also represent the grade, right? So that J will be 1, 2, 3, right? Then we can say that X11, X21, X31, and X41, right? That means that 1 is for regular, 2 is for premium. Let me use a different color. 1 is for regular, 2, then 3, right? Then 3. Right, so I'm just trying to represent this. Let me use a different color so that we can appreciate the variations here. So the variation here is that I'm using X11, X12, X1, sorry. So X21, X31, and x41. So 4 components in regular one. The same thing, x12, x22, x32, and x42. Then the same thing, x13, x23, that's component 2 in 3 because of these 3, x33, and x43. All right, so when we come here, right, we can still use our R, which actually make a lot of sense, or we get more meaning in that. So 12 times the regular. Remember, the regular is made up of x1, component 1 in regular, R1, plus x component 2 in regular, x component 3 in regular, plus x component 4 in regular. So we have this plus, so the 18 premium. So 18 multiplied by component 1 in premium plus x component 2 in premium plus x component 3 in premium plus x component 4 in premium. Right? Then we have low lead plus 10. X component 1 in low lead plus x component 1, component 2 in low lead plus x component 3 in low lead and x component 4 in low lead, right? Which is then the minus for the cost. So what's the cost here? It starts with 9. And what are the components? So 9 for component 1. So it means that 9 times, so 9 times x1 in regular plus x1 in P, or which is premium, plus x1 in low lead, right? So component 1 is found in all the various grades, the 3 grade. Then we also have plus, remember we have the negative on a big bracket, so everything is plus as it says here. 7 component 2. So what is component 2? x2 in regular, x2 component 2 in premium, then x2 in low lead. Then we have the 12 component 3. So component 3 in regular plus x component 3 in premium plus component 3 in low lead. Then finally 6 is component 4. So component 4 in regular, component 4 in premium, and component 4 in low lead. Then the big brackets comes here. All right. So if we continue to evaluate this, we don't even need to evaluate this at this stage. This is okay, right? But we can evaluate this. Okay, let's summarize this and see that. So max So max Z is, if you have to calculate this, you are going to have 3x1 regular 1 plus 5x component 2 regular 1 plus 6s component 4 regular 1 plus 9s component 1 premium plus 11x component 2 premium plus 6x component 2 component 3 premium. So 1, 2, 4, 1, 2, 3, and component 4, 12x component 4 in premium, then plus 1 component 1 in low lead plus 3 components 2 in low lead plus it's minus now, minus 2 component 3 in low lead plus 4x component 4 in low lead. So this is the objective function, right? So when the objective function is done, then what do we do? The second one, now we move on to the third one, which is the system constraints. It's the system constraints. So system constraints. So what are the system constraints? Remember, we have the number of components, 4 components, and maximum barrels available per day. Then the grade, the various component specifics. So let's do the maximum barrel available per day, right? So component 1, component 2, component 3, 4. We have the various maximum barrels per day. So if I'm to look at how many of component 1 can be found in regular 1, how many of component 1 can be found regular in premium, how many regular 1 component 1 can be found in low lead, then they should all be less than the 5,000 which were given in the question, right? So the first thing to do is that I have to state that component 1 in regular plus component 1 in premium plus component 1 in low lead, right, cannot exceed 5,000. Why? Because 5,000 is available. That's the maximum available barrels in a day. So you can get equal to the 5,000, but you cannot exceed it. Now, component 2 in regular plus component 2 in premium plus component 2 in low lead cannot also exceed 2,400, right? Component 3 in regular, component 3 in premium, component 3 in low lead cannot also exceed 4,000. Then we have component 4 in regular, component 4 in premium, and component 4 for low lead, which is the last one, cannot also exceed that. Now you can easily see that this on a high level can be written at the summation of let me get this right. So the summation of J, or let's say that Xij or X1J, right? Because these are 1, 1, 1. So XYJ, where J is moving from 1 to how many do we have? We have 3. Regular, premium, lead, low lead. So J is moving from that to that and is less than or equal to 5,000. The same can apply to this. So we have the summation here. Let me reduce the size of this so that the presentation will be great. So is summation here for X1J is less than or equal to 5,000, but J is moving from 1 to 3, right? The same thing, summation X2J, and is 2,400, and also J is moving from 1 to 3, RPL. Then also we have J moving from 1 to 3 for X3J, which is less than 4,000. Then finally, we have J moving from 1 to 3 again. Then is 4J and is 1,500. So either ways should be acceptable, right? On the high level, when you have big variables or decision variables, then you see that this section will be more appropriate to represent the constraints than this section, right? Okay, so we continue with the constraints. Now, after getting the components constraints, we should also look at the blending requirements. So the blending requirement says that regular should not less than 40% of component 1. What that means is that if you take component 1 in regular, right? If you take component 1, which is X1R in regular, the composition, that is 1 in regular plus 2 in regular plus 3 in regular plus 4 in regular, right? Not less than 40% means that 40% is the minimum. 40% is the minimum. So it means that it should be greater than or equal to 40%, which is 0.40, which is 0.40. So if you are to expand this, then you are going to get these constraints. XR minus 0.4 X1R minus 0.4 X2R minus 0.4 X3R minus 0.4 X4R should be greater than or equal to 0, right? However, looking at the linear programming, right? If you are to put it in a proper linear programming form, so we'll look at the general form of a linear programming. You see that this sign must always be less than when we are looking at a maximization problem. So this then becomes so 1R. So 1R. Let me see. Yeah, so we can solve this problem and see that and say that the final 1R, 2R, 3R, 4R less than that, so minus 0.6. So it means that this is supposed to be 0.6, then I will multiply through by negative 0.6 and multiply through by negative, so greater than or equal to 0. Pim, 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 pim. Okay, so it then is negative. So it's supposed to be 0.6 x1r, but multiplying 2 by negative, so 0.6 x1r x1r plus 0.4 x2r plus 0.4 x3r plus 0.4 x4r, and is less than or equal to 0. So something like that. So this is the form for a maximization problem for linear programming. Yeah, we'll look at that when we are looking at the properties of a typical linear programming model, or the general form of a linear programming model. All right, so the second constraint says that components 2 in regular should not be more than 20%. Should not be more than 20% means that it should be less than 0.2. That's what it means. So what this means that component 2 in regular for all the various components in regular, that's the mix, right, should be less than or equal to 0.2. What this means is that it should not be more than 0.2, but it can be equal to 20%. Right. So if you are to expand this, you are going to have, so multiply this by that and that by that, and it's 2 8. So this becomes positive. You take it from it and it becomes 0.8, right? So this goes to the left and it's 0.2 x1r, right, plus 0.8 x2r minus 0.2 x3r, and then 0.2 x4r, and it should be less than or equal to 0. Right? Okay. Then the third component specification in regular says that not less than 30% of component 3. So if I'm to take component 3 in the regular, right, for the entire components mix in regular, right, says that it should not be less than 30%. Again, it should be greater than or equal to 30%, which is 0.3, right? Which is 0.3. So again, if we are to expand this and also produce it in the general form of the linear programming, then we are going to obtain 0.3 x1r plus 0.3 x2r minus 0.7 X3R plus 0.3 X4R and is less than or equal to 0. Okay. Now we move on to the premium. Premium says that the constraint is that the component 3 should not be less than 40%. So component 3 in P, component 3 in P. So it means that the component mix 1 in P plus 2 in P plus 3 in P plus 4 in P should not be less than 40%. Means that it should be at least 40% and above. Right? It should be 40% and above. So if we are to work this thing out and put it in the general form, then we are going to get 0.4 x component 1 in P plus 0.4 x component 2 in P minus 0.6 x component 3 in P and plus 0.4 x component 4 in P, and it should be less than or equal to 0. Then the low lead, we have two conditions here. Low lead. Component 2, not more than 50%. So not more than means that it should be less than 50% or equal to 50%. So component 2 in low lead. So 2L, right? Yeah, 2L in the component 1L plus 2L plus 3L plus 4L, right? Should be less than or equal to 50%, which is 0.5. And if it is 0.5, and we have to work this thing out, right? Already is in a general form of the linear programming or of the LP. So if we are to work things out, there is x2L, so that's 0.5, so it's positive 0.5. So I'll have negative 0.5 component 1 in low lead plus 0.5, 0.2 in low lead minus 0.5 component 3 in low lead and 0.5 component 4 in low lead, and is less than or equal to 0. Then the last one is that the component 1 in low lead should not be less than 10%. So 1 in low lead for all the various components, 2 low, 3 low, 4 low, should not be less than, so it should be greater than or equal to 10%, 0.1. 0.1. So if we are to expand this, then we have 0.9, 1 in low lead plus 0.1, 0.1 x component 2 low lead plus 0.1 component 3 low lead and plus 0.1 component 4 low lead, and should be less than or equal to 0. All right. Then, as usual, we have the non-negativity rule, which is Xij should be greater than or equal to 0. Greater than or equal to 0. So, in summary, right, the model is actually one. I want to maximize the profit, which is Z, and is 3x1r plus 5x2r plus 6x component 4 in R. So we are finished with the regular. Then move on to 9x component 1 in premium plus 11x component 2 in premium plus 6x component 3 in premium plus 12x components 4 in premium plus x component 1 in low lead plus 3 component 2 in low lead plus minus 2 component 3 in low lead and 4 components 4 in low lead. Okay, so after determining the objective function, then we'll, as usual, say that this function is subject to, then we list the various constraints. So it's subject to x1r plus x1p plus x1l and is less than or equal to 5,000. Then the second one is x1, which is here, to r plus x to p plus x to l is less than or equal to 2,400. Then x, so the x here is x to the l is 0 here, right? So to put it on the line is x to the r plus x to the p plus x to the l is less than or equal to 1,500. Then 0.6 x1r minus x21. So x21, so minus 0.x2r. Now, sorry, so we have already converted this into the form, which was negative 0.6 x1r plus 0.4 x2r plus 0.4 x3r . minus 4x for r, and this is less than or equal to 0. Then we have negative 0.2 x1r minus plus 0.8 x2r minus 0.2 x3r, then negative or minus 0.2 x4r less than or equal to 0. Then we have 0.3 x1r plus 0.3 x2r minus 0.7 x3r, and then plus 0.3 x4r less than or equal to 0. Then minus, second one is here. Move this out. 0.41p okay, so plus 0.4 x2p minus 0.6 x3p, then plus 0.4 x4p, and it's less than or equal to 0. Then we have negative 0.5 x1 1L. Okay, so 1L. So let me move it under this. Yeah, so usually you want to arrange them into the various lines. Yeah, I make some few lines. So I should have opened this up, but that's fine. At least you are getting the concept, which is fine. So it's negative 0.5 x1L plus 0.5 x2L minus 0.5 x3L, then minus 0.5 x4L less than or equal to 2. Just trying to get it right. All right, the second one is 0.9 x1L minus 0.1 x2L, 0.1 x3L, and 0.1 x4L 0. So I'm converting that, and that. All right, so when you look at the constraints, we have the number of barrels for the 4 constraints. So this is what I usually do. So I can say that xij is greater than or equal to 0. So I have to check the various constraints to see whether everything is right. So I have the 4 components, 5, 24, 15. So I mix the third component. I mix the third, so 1, 1, 1, 2R, 3R. So 3R is 2, 4,000, right? Then, so this is why it's always good to check before you closing. So the other one is 1500, and it's for the fourth component, which is X for R plus X for P plus X for L, and that is 1500. So let's capture this one. 1500, and the other is 0. All right, so I have my 4 constraints here for representing the 4 components, which is good. So you want to always ensure you have this. Then regular, the component specifications, we have 3, not less than 40%, not more than 20%, and not less than 30%. So the 3 for regular. So components specification for regular, spec for regular. Then I have 1 premium. I have 1 premium, so component specification for premium. Then I have 2 for low lead, 1, 2. So component spec for low lead. And then the non-negativity. So I am certain I have covered all the various constraints that are required for this model. So this is a typical model that has been developed. Yes, so don't worry about how it can be solved, but we will be able to solve this. All right, so now let's look at this next example. The next example. So I will close the whiteboard and share my screen for and we can read the next example. All right, so I believe we are all getting the understanding. So this is related to double subscripted problems. All right, so this is an investment question or problem. An investment firm has is it 10 million or 1 million? 1 million. Yes, 1 million. So let me. Yeah, so $1 million to invest in 4 alternatives. What are the alternatives? Stocks, bonds, savings, certificates, and real estate. The firm wishes to determine the mix of investment that will maximize the cash flow at the end of 6 years. So investment opportunities in stocks and bonds are available at the beginning of each of the next 6 years. Each dollar invested in stocks at the beginning of each year will return $1.2. That is a profit of 0.2. 2 years later, and can be immediately reinvested in any alternative. Each dollar invested in bonds at the beginning of each year will return $1.4. 3 years later, and can be reinvested immediately. Investment opportunities in savings certificates are available only once at the beginning of the 2nd year. Each dollar invested in certificates at the beginning of the 2nd year will be returned $1.8 4 years later. Investment opportunities in real estate are available at the beginning of the 5th and 6th years. Each dollar invested in real estate will return $1.1 or $1.10 1 year later. Now, in order to minimize risks, the firm has decided to diversify its investments. The total amount invested in stocks cannot exceed 30% of total investments, and at least 25% of total investment must be in savings certificates. So the management of the firm wishes to determine the optimal mix of investments in the various alternatives that will maximize the amount of cash at the end of the 6 years. So this is a typical investment problem. That's application of operation research or linear programming in the financial sector. So let's see how we can model this this problem in a linear optimization environment. So let me stop sharing my screen and bring the whiteboard here. Let's continue from where we ended, and let's get a new page for this so we can begin solving this, formulating this problem. So usually for us to appreciate this problem, let's graph the problem. So let's represent the problem in a diagrammatic, or in a pictorial view, so that we can appreciate this whole theoretical narratives of the problem, right? So assuming we want to use, okay, let me use black in this case. So let's use these lines to represent the number of years. The number of years, right? The number of years. So I will say that I have year 1, I have year 2, I have year 3, year 4, year 5, and year 6. All right, so we are told we have 6 years, right? So the first thing to do is to determine the decision variables, right? To determine the decision variables. So we can quickly define the decision variables. Let's say that I want to use S to represent the amount invested in stock, right? So amount invested in stock, we are told that it is invested in stock at the beginning of each year and will return 1.1. So beginning of each year means that I have stock 1, beginning of the year. I have stock 2, right? And when you invest in stock, you get your profits and your money back in 2 years. So stock 1, when I invest, I'm going to get my return and do investment in stock 3. 2 years time, I'll get my return and do investment in stock 5. So beginning of each year, right? Then 2 years time, I'll get my final return in year 6. However, I'm not going to invest it, so it's not a decision to make. That how much should I invest? How much should I invest in year 2? Will return in year 4. Then how much should I invest in year 4? Then how much should I invest in year 6? Now, I won't be able to invest in year 6 because if I invest in year 6, I'm going to get my return in year 7. But year 7 is not part of our decision, or we only have 6 years to do the investment. That means that year 7 cannot be an option, or year 6 cannot be an option. So the decision is in year 2 and year 4, right? How much should I invest in stock? So you present these decision variables because you don't know how to, solve them, or you don't know how to determine this particular problem. You don't know how to solve it. So you present the decision variables. Later on, when we want to solve it, then we'll be able to determine how We can solve this by it's pretty simple. Yeah. Then we look at bond. Bond is available at the beginning of each year. So you think that we can have bond 1, bond 2, bond 3, bond 4, bond 5, bond 6, and so on. However, it says that each dollar you invest in bond at the beginning will return 3 years later, meaning that I have my bond 1. Bond 1 will return in 3 years later. So year 1, year 2, end of year 2, then end of year 3. Right? End of year 3 is the beginning of year 4. Assuming I invest in that, which is B4, that is in year 4. 3 years. So 1, end of year 4, 2, end of year 5, 3, end of year 6, which is good. Now, when I look at B2, remember it says that it's available every year. You need to consider that investment opportunities in stocks and bonds are available at the beginning of each of the next years. So I think that B2 is a decision that we can make. But how much should I invest in B2? I don't know. That's why we want linear programming to solve for us. So we are creating a decision variable in year 2 that is an option or it's a decision to make, but I don't know that decision that must be made. However, in 3 years, so end of year 2, end of year 3, then year 4 will be 3 years. So 1, 2, 3. Can I invest here and say year 5? No. Why? Because 1, 2, 3, it moves us into year 7. However, it will return in 3 years. So it's not an option. It's not, we don't want to make a decision that how much should I invest in bond in year 5. So B5 is not an option or cannot be a decision that we want to make. That's why there is no B5. But there can be B3. Why? Because end of year 3, end of year 4, end of year 5. 3 years time, I'm getting something. Again, when you have your B6, end of B6, you can see that it goes beyond 3 years is somewhere here. And therefore, how much should I invest in year 6 should not even be a decision to make. So B6 is not an option. So you can see that for bonds, we have B1, B2, B3, and B4. Now, savings certificates. The question says that savings certificates are available only once at the beginning of year 2. So only once at the beginning of year 2 means that if, let me use red so we don't get a lot of blue scribbles on the picture. At the beginning of year 2, it means that C2 can only be here. And how long can it go before we can get our return in terms of our initial deposit and the profit? It says that each dollar invested in certificate at the beginning of year 2 will return 1.8 4 years later. So 4 years later, beginning of year 3 is 1 year, beginning of year 4 is 2 years, beginning of year 5 is another year, and that's so 1, 2, 3, 4. It ends here. That's the only condition we have. Then it says that real estates are available at the beginning of the 5th and the 6th year. Each dollar will return 1 year after. The beginning of the 5th and 6th year. This is the 5th year. Real estate, let's use R. So R5 is for real estates, and we'll say that year 1, 1 year time, you get your money. Then I can also invest in R6 and say that how many should be invested in R6 so that I can return by the end of year 6. So basically, these are the decision variables that we can concern ourselves with. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12. So this is a pictorial view. So the objective function here, the first one is the decision variables. So number one, what are the decision variables that must be considered in this program? So the decision variables is that we should let SI, right? This is money, so we'll use amount. Let XI be amount and not quantity. So be the amount of money, right, invested in stocks. Invested in stocks at the beginning of year I, right, beginning of year I, where I is 1, 2, 3, 4, 5, right? Then let's BI be the amount of money, right, invested in bonds, right, at the beginning of year I, where I is, how many bonds do you have? 4. So we'll say that I is 1, 2, 3, 4, right? Let's see, C is just 2. So is the amount of money invested in savings certificates. Savings certificates, right? And it's at the beginning of year 2, which is straightforward. Let RI be the amount of money invested in real estate, right, at the beginning of year I, where I is 5 and 6, right? Then it's very likely that there may be some amount that we are not investing at all, which is idling. So every year, there may be an amount that are not being invested at all. We want to know that amount as well. So that could be I. So I is amount of money, held idle and not invested at the beginning of year I. At the beginning of year I. I think this is straightforward. All right. So after receiving variables, the second thing is what? The objective function. Is the objective function. All right. So what is the objective function? At the end of the year 6, what money do we have? Let's go back to our pictorial drawing. Now, at the end of year 6, we'll see that we have, let me use black to represent this. We have S5, red should be clearer. We have S5. We have B4. And we have R6. Then surely these 3 plus the money held idle. So these will form the final, money, or you say that the management of a firm wishes to determine the optimal mix of investment in a various activities that will maximize the amount of cash at the end of the 6 years. So at the end of the 6 year, we have money coming from X6, money coming from B4, money coming from R6, and the idle money, I6, that we had not invested. So this will be the objective function. So the objective function is to maximize Z, which is the stocks. Stocks says that when we invest in stock at the beginning of each year, it will return 1.2 at the beginning of 2 years, right? Or 2 years later. And it's the return, and we want our total money, not the total profit. It's the maximize the amount of cash. So total money, which includes what was invested plus the profits. So I will use my $1.2, right, times stocks for year 5, right? Stocks coming in from year 5, S5, plus bond. Bond is 1.4, B4. Then real estate is 1.1, R6, and the amount being held idle, right? The amount being held idle, right? Again, if we are to present this in any form or in the general form, it will be XZ 0x1 plus 0x2 plus 0x3 plus 0x4 plus 1.2x5 plus, we have S's? No. 0B1 plus 0B2 plus 0B3 plus 1.4B4 in that order, right? So that we'll put all the various constraints under each, right? Okay, so if you understand the principle, I don't think we should worry our head, or we should spend more space to present that. I just want you to understand this, that usually you want to arrange your constraints under the objective function, right? All right, so we will maintain what we have here, right? And say that, what are the constraints? So we have the yearly constraints, right? What are the yearly constraints? When you look at the pictorial, we'll see that in year 1, we have S1, S2 plus I1. That's the money which is held in idle, which is not being invested. So when we come to the 3, which is the constraints, system constraints, right? So the first one will be in year 1. In year 1, what do we have? We are investing in stocks, we are investing in bond, and we have money which is idle. And this will be equal to the 1 million that we have. This is the first constraint. It's equal to the 1 million that we have. Then we talk about year 2. Again, go back to the pictorial. We have S2, B2, C2, and again, I2. Now, you can see that S1, B1 are not returning anything in year 2. That means that the money available in I1, that's the money that was held idle That is the only money that will be available to be invested here. Plus maybe let's leave another one, right? So when you come here, I2 will be made up of S2 plus B2 plus C2 plus I2 and is equal to I1. See, my eyes are too big. It's equal to I1. Now, in year 2, you see that we will have another set of constraints. You can go back to our pictorial drawing and see what we have here. In year 2, the beginning of year 3, we have S3, we have B3, and again, we will have I3. So we have S3 plus B3 plus I3. However, this will be equal to, so how much am I investing will be equal to what is coming from S1. What is coming from S1? When I return in S3, should I invest what is coming or I shouldn't? I don't know, but you have to present it in the equation. So, or should I invest it in B3? I don't really know. So what you do is that you say that then it's equal to what is coming, which is 1.2 S1 plus whatever that was, or that was remaining from I2. I2. All right. In year 4, you see that we have S4 plus B4 plus I4. It's equal to 1.2 S2 plus 1.4 B1 plus any money that was held idle. So year 4, beginning of year 4, we have S4, B4, and I4. S4, B4, I4. However, we have S2 coming here, and we have B1 coming here. That's why we have S2 coming here and B1 coming here, plus that. Okay, then in year 5, we have S4, S5, see, here is this S5 and R5. That's what the decision we want to make. Plus, how much should we leave idle? I5. So we have S5 plus R5 plus I5, right? And this is returning, S. So we have, okay, so from the pictorial view, you see that we have S3 coming in here and B2 also coming at the year 5. That means that they are the money that will be available. So should we take a decision? We don't know. So we just have to represent them and say that 1.2 S3 will be available, 1.4 B2 will also be available, and the previous year's money that was held available, that was held idle, will also be available. Then lastly, we'll have our year 6, which is year 6. We can see year 6. We are actually having R6. So only R6 must be invested. So we'll say that R6 must be invested plus I6. How much should we keep idle? And these are all what money will be available. 1.2 S4 plus 1.1 R5 will be available plus 1.8 C2 plus 1.4 B3 plus I5, right? So you see we have S4 coming in at this point. We have B3 coming at this point. We have R5 also at this point. And before we have I5, right? That is not idle. So that's why we have S4, B5, C2, B3, and I5. S4, so S4, B3, B3, yeah, that's it. I'm just trying to confirm everything. R5 also coming in here. C2, where is C2? Where is C2? Yes, C2 also coming in here before the money that is idle. So you need to look at the constraints you have, right? Then we have the management policy. What are the management policy? The management policy is that in order to minimize risk, the firm has decided to diversify its investment, saying that the total amount invested in stocks cannot exceed 30% of total investments, cannot exceed total investments. So the total amount, remember we have used the summation before. So we are saying that the summation of total amount in stocks, right? Total amount in stocks, which is from I1 to 5, because S goes from S1 to 5, right? Cannot exceed means that it's less than or equal to 30% of the total investment. The word total investment, 0.3 times the total investment. Total investment is made up of summation of 0.3 SI, I is equal to 1 to 5, plus summation BI, I is equal to 1 to 4, because we have B1, 2, 3, 4, plus C2, plus summation I is equal to 5 and 6, that's for R. So this, that policy, the total investment. Then, which other policy do we have? We have another policy on the saving certificates. That says that the 25%, at least 25% of total investment must be in savings, must be in saving certificates. So saving certificate is C2. So C2 should be greater than or equal to 25%, which is 0.5 of the total investment. So again, summation I is equal to 1 to 5 for XI, plus I is equal to 1 for BI, C2, I is equal to 5, 6, I, that, right? So this is the problem. Which other one do you have? Non-negativity. Non-negativity. So it means that non-negativity is SI should be greater than or equal to 0, BI greater than or equal to 0, C2 greater than or equal to 0, and RI greater than or equal to 0. So that's it. So later on, then you now present this in the linear programming model form, where you say that I want to maximize Z, and it is 1.2 S5 plus 1.4 B4 plus 1.1 R6 plus the money that was available in the year 6. And you say that this is subject to the various, all the constraints all the constraints where you see S1 plus B1 plus I1 is equal to 1 million, right? Then you see S2, B2 plus C2 plus I2 minus I1 is equal to 0. So you try to bring it in the general form of the LP. B3 plus I3 minus 1.2 S1 minus I2 is also equal to 0. S4 plus B4 plus I4 minus 1.2 S2 minus 1.4 B1 minus I3 is equal to 0. S5 plus R5 plus I5 minus 1.2 S3 minus 1.4 B2 minus I4 is equal to 0. R6 I6 minus 1.2 S4 minus 1.1 R5 minus 1.8 C2 minus 1.4 B3 minus I5 is equal to 0. Then we'll have the other constraint 0.7 times summation I to 5 SI. That's the policy. I is equal to 1 to 4 for the BI. 0.3 C2 minus 0.3 I is equal to 5, 6 II less or equal to 0. Then we have 0.25 summation I is equal to 1, 5 SI plus 0.25 I is equal to 1 BI minus 0.75 C2 plus 0.25 summation I is equal to 5, 6 RI less than or equal to 0. Then we see that SI, BI, C2, RI is greater than or equal to 0. So this then becomes the general form of the problem, the general form of the problem. Yes, general form of the problem. All right, so I'll close this and I will share my screen and we'll continue with the general form of a linear programming model. So you see clearly that a typical linear programming model would have a maximization or minimization problem, and it will be represented as the coefficients of the objective function for the various decision variables, and is subject to a set of constraints which could be less than or equal to, or it could be equal, less than or equal to, or equal sign, or greater than or equal to, and it's to the right hand side, which are the BIs. Now it's notable to note how we are using the variables or the coefficients here, or the signs, the symbols here. So I'm using C to represent the coefficients. I'm using double subscripted A1, 1, A1, 2 for the resources, and also the BIs as the resource limits, right? So these are for the constraints. And we are saying that J may be from 1, 2 to N, I may be from 1, 2 to M. And we have some contributing factors here. Factors here, and also CJ, contribution per unit activity. So these are the CJs. Yeah, very important. Note them here because we are going to use them in the future. The BI is the amount of resources available, and the AI is the amount of resources that are consumed by each activity, right? So that is a general form of the linear programming, right? All right, so I think we'll pause here. So in our next lecture, we'll look at the properties of the general linear programming model, and then we will look at some of the problems that we can solve. Then we'll start solving them linear programming. We'll start solving the linear programming problems. All right. Well, I think I can even look at the properties today. So in order to evaluate how well linear programming applies to any given problem, some assumptions of linearity should be satisfied to a large extent. So linear programming models ensure that or assume that there is some element of linearity. So sometimes it's not applicable to geological variables or some natural occurring variables, which are usually nonlinear. But if they appear to be linear, then we can use the linear programming to solve that. So we can assume that there is proportionality. This implies that the rate of change or the slope of the function, right, relates to a constant. So there is a relationship between the rate of change, and therefore changes of equal size in the value of a variable result in exactly the same relative change in the functional value. So it means that any change will affect the results. That's what the proportionality assumption means. So for instance, if AII is 5 and XI is equal to 2, then AII times XI is equal to 10. That's what it means. So the left-hand side will proportionately change with the right-hand side. That's what it means. Then additivity, meaning that there is an assumption that there is no interaction between of the activities, so that there are no cross product terms in the model, right? So what that means is that, for instance, a total function value can be obtained by adding the individual contributions from respective activities, right? So we can say that Z is 3x1 plus 5x2, and x1 is 1, x2 is 1, and therefore Z is equal to 8. That's what it means by additivity. And therefore, divisibility is also assumed that activity unit can be divided into any fractional levels, right? So that non-integer values for decision variables are permissible. So we can get non-integer value that is positive values that are non-integers, which can be less than 1 values, or positive and negative values. But remember that our like continuous values, but remember that our non-negativity will ensure that we don't get any negative values or negative integers, right? Great. Then also we assume certainty. Means that all the parameters of the model are known constants. So they are known constants. However, the content or the value itself is unknown unless we solve them. So we assume that they are known. Either they can be 0 or they have a particular value assigned to it, right? And we also say that there is a degree of uncertainty, especially as the parameters will be used to predict future conditions. So though they are known, there is some degree of uncertainty in terms of we don't know what the value will be like, right? But it can be used to predict the future conditions, right? So We assume that the values are known. However, they are known constants, but the value itself also has some element of uncertainty in it because we don't know the exact values that represent each parameter, right, or each of the constants. So because of that, we could conduct sensitivity analysis. So sensitivity analysis is normally conducted as one means of accounting for the uncertainty. So we do sensitivity analysis on these parameters so that we can know the form of certainty that we have. All right, so by way of assignment, the students is challenged to solve this problem and to submit it per the instructions provided in the VLE. That's our visual learning environment. So Mer Company has 2 truck manufacturing plants. The 2 plants have the capacity for producing 2 types of trucks. The net unit profit for producing the truck types 1 and 2 are $4,000 and $3,000 respectively. Plant 1 and 2 have the capacity to produce 700, 900 trucks per year respectively, regardless of the type of combination involved. The amount of available space also imposes a limitation on the production. So students are supposed to formulate a linear programming model for this problem, and it's a maximization problem. Yes, a maximization problem. So this is where we will end this lecture, and the next lecture we'll look at how we solve linear programming problems using the graphical method, using the simplex method, and also the two-phase method. So I want to thank you for staying with me up to the end of this lecture, and prepare yourself, solve the 2 questions in the handout. The first one is on this slides, and also the second one is shown in the handout. Solve it, submit your solution to the VLE platform, and we'll give you some feedback. Then we can look at solving the linear programming problems in the near future or in the next lecture. So thank you, and do have a very good day. All right. Bye-bye.